Right. Hi everyone. My name is Zyskind. I'm the CEO and co-founder of Enigma. And today I want to tell you about secret contracts. I want to tell you what they are, so we'll define them. I want to explain to you how they work. But most importantly, I want to tell you why secret contracts are crucial to actually build a more private and more scalable decentralized internet. Not sure this is working. Yeah, it's not working. Yeah, no. Thanks. Thank you. All right. So let's start with some context about blockchains and smart contracts. This is very high level. I'm sure all of you know this. So what really gets us excited about blockchains is this idea that we can run applications not on one computer, not on a centralized server, but instead we can run it across thousands and thousands of computers. And through a process known as consensus, these computers can make sure that the applications that they are running, the databases, and all that stay in consistent sync. Now, why is that important? Well, think about an adversary that wants to attack the application. Well, that adversary is going to have to basically compromise the entire network to be able to do some damage. So if you think about Bitcoin, for example, Bitcoin has a shared ledger of transactions, and we feel much more comfortable that it's being maintained by thousands of computers because it makes it much, much harder to actually tamper with that ledger in any significant way. And smart contracts, for the sake of this talk, are basically units of code that developers can deploy to build applications that run on the blockchain. Okay, so blockchains are great, but they have several, I'd say, show-stopping problems. One of them, which you all know, is scalability, but one that is often overlooked is the problem of privacy. Everything that you have on the blockchain is completely public for everyone to see. That's by design. Now, the problem with this is that if we want blockchains to become the next iteration of the decentralized web, we have to find a way to handle sensitive data. All of our applications that we use on a day-to-day basis right now use sensitive data in some form or another. And blockchains cannot differ in that. They have to be able to do the same. So, this is where the definition of secret contracts becomes helpful. So if smart contracts, for example, on Ethereum, give us this property of correctness, it gives us this property that no one can tamper with the state of the smart contract, with whatever is going on with the smart contract. The question comes, what is the definition for something that also protects privacy? And that's where we call this secret contract, because it both can achieve correctness and protect privacy of the data. And Enigma sets out to be the first public network that allows you to write secret contracts efficiently. How secret contracts work is by allowing or making sure that the computers in the network don't actually get to see the data that they're operating on. So encryption is a fairly known and solved problem for the last few decades. We know how to encrypt data at rest. So if you want to encrypt your files and put them on a storage, you're good. But the question comes, how can you take data, manipulate it, use it in some processing, like on a blockchain setting? How can you do that without actually leaking any information to the nodes? So we need some kind of technology that allows us to compute over encrypted data. And we've been working on this for several years. Enigma started back in the day in 2014 as a research project at MIT. 2015, we published 2 papers around blockchain and privacy. These papers became really popular. They stand at about 500 plus citations combined, which make them among the most cited in the space. And they really laid out this idea of how can we build more scalable execution for blockchain, but most importantly, how can we maintain the privacy of the data. And kind of fast forwarding to today, in the last, I'd say, year and a half, we've been working on the first platform, the first public network that allows it. The first version, you can think about this as Enigma 1.0, is called Discovery, and it's going to be the first one that allows you to actually run secret contracts. It has other important properties, such as it's being permissionless, so any one of you will be able to download the Enigma node, put some stake in Enigma tokens on the blockchain, and then start contributing computational resources in return for fees, which also applies to it being economically incentivized. And the last part is that it's compatible with Ethereum. So we recognize that Ethereum right now is the most secure and widely adopted chain, and we don't want to make developers have to choose between Ethereum and Enigma. So there is a very seamless bridge that allows you to write your smart contracts on Ethereum, but then if you want to offload both sensitive, computations that involve sensitive information or that require scalability, you can do that in a seamless way to Enigma and back to Ethereum. So I'm gonna go deeper now. First, let's talk about the stakeholders. There's developers, users, and workers in our network. Developers, as usual, write secret contracts. So they develop it, and then they deploy it to the network. Users submit tasks. That's how they interact. Through tasks, they interact with the secret contracts. And then workers, and we call these workers to distinguish them from Ethereum miners or blockchain miners in general. Workers are actually taking these tasks and these secret contracts and actually execute the code and do the computation. So from a developer's perspective, we support Rust, or more correctly, WebAssembly, and we support Solidity. The entire industry is moving to WebAssembly. That's something that I hope most of you know, or if not, you should. So we're focusing most of our efforts in that. Ethereum is no different. Ethereum is going to move to WebAssembly, or one notion of it in Ethereum 2.0. But still, to be backward compatible, we also allow you to write your contracts in Solidity. And then once a secret contract is deployed on the network, users can interact with them with tasks. A task is very similar to a transaction on Ethereum. The main difference is that the user can encrypt all of the inputs to that smart contract, to that secret contract. And this is done through the Enigma.js library. It's very similar to Web3.js, so it should be very, very familiar for developers and easy to use. And it obfuscates all of the complexities of key exchange and encrypting on the client side, etc. Now, where the magic happens is once a task is being sent to the network, now the workers need to execute it. Now, the important part to understand when it comes to scalability is that unlike blockchains today, unlike Ethereum and other blockchains, we don't require the entire network to replicate the computation. That's very costly, that's very slow. Instead, the network runs a lottery and samples by stake a group of workers to do each computation. So say that group is 20 nodes, those 20 nodes and only they are going to run that computation. And that allows you to basically get some form of sharding and allows you to parallelize computations and get a lot more throughput. Once the computation is completed, what the workers do, they submit a very succinct, very short proof of computation back to the Ethereum blockchain. The Ethereum blockchain does some very quick on-chain validation, which is very cheap and very fast, that's important. And if that computation is correct, then the workers get paid with the NG tokens. When it comes to encryption of data and how that flows in the computation, so users can supply encrypted inputs, as we said. Users can get encrypted outputs in return, but also the secret contract itself has an encrypted database. And like Ethereum, which has a state database, in here each secret contract has an encrypted state database. And the important part to realize is that the nodes in the middle, the ones that are actually running the computation, never get to see the data. They only operate on it, but they don't see the inputs, the outputs, or the state database. So far I told you a lot about encrypted computation, but I didn't really touch about how that's happening. Given time, I'm gonna kind of squeeze it and just talk at a very high level. But currently in Discovery, the main idea to get this done is by using something called a trusted execution environment, or a T. A T is basically a sandbox region in the processor. It's available in all modern processors. And it basically ensures that every computation that happens inside that region of the processor cannot be tampered with, and no one can see the data that's going on inside, even as processing being done. So that's really how we achieve privacy. Everything gets encrypted on the outside, sent to workers that run these Ts, and only inside of these Ts, the information gets decrypted and computed over. But even if you're the host, even if you're the owner of the machine, you cannot see what's going on inside, and then data is re-encrypted, the results are re-encrypted and sent encrypted to the outside. So this is great, it's very fast, it's very scalable, but it's a hardware solution, not quite a cryptographic one. If you want even stronger cryptographic solution, then there are two known techniques in academia today, and usually they're referred to as the holy grail of cryptography. One of them is secure multi-party computation, or MPC, and the other is fully homomorphic encryption, or FHE. Both of them achieve pretty much the same thing, but in very different ways. They allow us to compute over encrypted data, but MPC is orders of magnitude more scalable today, and I've been personally researching MPC for the past few years. My thesis was on that. So for these reasons, we're focusing on developing MPC for the Enigma network in the next iteration. One very quick comment about zero-knowledge proofs and like ZK Starks and ZK Snarks. They're great technology, but it's an often misconception that they solve the privacy problem completely. What zero-knowledge proofs allow you to do is to prove some computation over data that you can see. But someone still has to see all the data. They do not really allow us to compute over encrypted data. All right, so MPC just in general, it's the idea that if we have a network of computers, then it's mathematically proven that that network can run any computation on the directly encrypted data without decrypting it in any step, as long as one node in the network is honest. So let's say you have a network of 1,000 computers. If one of them is honest, it doesn't matter which one, data is going to remain encrypted at all times. And we're working about plugging this kind of back into Enigma. We're working on this right now. The idea is basically that we don't really have to change much in the network. It's really all on the backend stuff, on how nodes in the network interpret opcodes. And that's something that's going to be public in the next version of it. So any technology is really only as useful as the applications that people are building on top of it. This is just a short list of several applications that real companies in the space are building on us right now. And that's actually a very short list. There are many more suggestions and many more projects that are building beyond that. I want to talk about two in particular. One is secret voting. So voting is a super important building block in blockchains because a lot of projects want to do decentralized governance in one form or another. But again, if you think about Ethereum or any other blockchain today, the problem is that all the information is public. So that means that if you have a voting smart contract, that means that everyone is going to be able to see who voted for whom. And that's obviously a deal breaker, not only to people's privacy, but it also leads to very expensive attacks like bribery attacks and vote censorship attacks. So that's really bad. And already several companies like Aragon and Ocean are building their version on our platform for secret voting. Another cool use case is with EximChain, which involves machine learning over encrypted data. And with the EximChain example, they're focused on doing machine learning for credit scoring. And what they want to do, they want to make sure that all the data, all the financial data that goes into credit scoring is completely private. And not only that, they want to make sure that the model that is being learned through this machine learning remains encrypted, because that model is really the secret sauce of their algorithm, of what they're building. So on the right, that's the actual code that's doing this, and on the left is what the result of this would be. Now, Enigma is out right now in testnet. If you're a developer and interested, really all the information that you need is at enigma.co/protocol. But if you want to get even more involved, there are several ways to do it right now, as we are ramping up for mainnet in the next few months. We just released our grants program, so if you want to contribute something to the ecosystem, these are very well funded, and you should get in touch. If you're a developer, you can get early access to our development material and start building. But if you're not a developer and you just want to run node in the network, then there's an early access link for that as well, which I welcome you to use. But if you're interested in staking and generalized mining, this is probably the best way for you to go, because Enigma is going to be one of the first networks that allows this kind of staking for rewards model in the wild. That's it on my end. Thank you very much. There's time for one question, if anyone wants.
What do you think about the concerns and the risks that have been identified in enclaves recently? And do you think we're going to be able to provide mitigation factors around that?
Sure. Sure. So I guess, first of all, yes, I think there will be provided mitigations. I think enclaves are a very recent technology. They're not that new, but when it comes to general purpose computing, they are very recent. And I think right now it's really in the formation and implementation phase, and there are constant improvements. On our end, we're tackling these from two angles. First of all, that's why we're selecting multiple workers, right? So that you still need to reach consensus across workers, so that even if someone spends a lot of money to kind of break an enclave, they're still not going to be able to break the computation. For privacy, it's still going to be an issue, but that's also why we're working on other technologies like NPC. All right, thank you very much.
All right, thank you very much.